If we have two 30, 60, 90 triangles, you in fact know that these two triangles are going to be similar because of a similarity theorem. You'll notice that in each triangle we have a right angle, in each triangle we have a 30-degree angle, so these triangles will definitely be similar, which means that sides are going to be in proportion. This is not a surprise because we have been finding sides of 30, 60, 90s, so you know that with the bigger triangle, if the shorter leg is 4, the longer leg is 4 times the square root of 3. And likewise in the smaller triangle, the longer leg is 4 times the square root of 3. So if we want to find the ratio of sides, say smaller leg to longer leg, smaller leg to longer leg, it is not a surprise that we end up with exactly the same number, right? Shorter leg to longer leg, we end up with square root of 3 over 3, which is to be expected. These two triangles are similar, so it's not a surprise at all. What is a little bit of a, not a surprise, a little bit of something new, is that if we had two triangles that weren't 30, 60, 90 triangles, suppose we have a right triangle with a 20-degree angle and another right triangle with a 20-degree angle, except this one's going to be smaller. We know that these two triangles also are going to be similar, so that if I was going to take the ratio of sides, A to B in the big one, you know that that's going to be equal to C to D in the smaller one. And this ends up being really unbelievably handy. But rather than talk about a long leg and a short leg, what we're going to do is talk about something called a tangent ratio. And for a tangent ratio, we always take a right triangle and we position ourselves at one of the angles. So let's imagine that we're going to position ourselves right in here. We're sitting right in angle A. And the other thing that we use with right triangles is capital letters refer to angles and lowercase letters refer to lengths of sides. So the side that's going to be opposite, angle A, so right over here, I'm going to call this side A, lowercase a. And if we're at angle B, this side that's opposite angle B, right over here, I'm going to call lowercase b. And the hypotenuse I'm going to call lowercase c. And what we're going to talk about is a ratio of sides. So anytime we have a similar triangle, I'm going to say the tangent of angle A, tangent is defined as the opposite leg over the adjacent leg. So if we're seated right at angle A, the opposite leg is going to be A, the adjacent leg is going to be, well, the one right next to it. We're leaving hypotenuse out of this for right now. So tangent is defined, tangent of some angle, I'm going to call that theta, Greek letter theta, is defined as the opposite leg over the adjacent leg. And likewise, if we were going to find the tangent of angle B, well, the side that's opposite that is side B, and the leg, the adjacent leg, is side A. So tangent for any angle is defined as the opposite over the adjacent legs. And keep in mind, we only find tangents of acute angle. We don't even bother finding the tangent of angle C for a very complicated reason. So that's a little introduction to tangent.